Hi, I've got a presentation to show you today about solving Pell's equation. We're just going to start with Diophantine equations, which are equations which are polynomials and only integer solutions are considered. And that means polynomials are equations that only involve adding, subtracting, multiplying, and powers of variables are only positive integers. So, for example, y squared equals x squared plus 3. That is fine, that's a polynomial equation, but something like x to the 3 halves plus 3 equals z wouldn't be, because 3 halves isn't an integer power. And you can have as many variables as you want in your polynomial equation. It doesn't matter, it doesn't have to be just 2. And the fact that only integer solutions are considered, that means that in certain situations we can gain more information about an equation, and that could lead to a set of unique solutions. And some applications of these equations are balancing chemical equations in chemistry. And this is a basic example that you've probably all seen before when you've done GCSE chemistry. And you can balance that quite easily by looking and by inspection. But if you have a look at chemical equations like this, then you can see how it's much harder to do so. And that's where these Diophantine equations can come in useful. And they also can be used in elliptic curve cryptography. And this is an example of an elliptic curve there. And you can see that the equation of an elliptic curve is a polynomial. And in cryptography, x and y, they will be taken as integers. And also, in reality, lots of variables will have to take integer values. For example, the number of students in a classroom, the quantity of a certain item that's being ordered, or the number of a certain atom in a compound, as we saw before. Now moving on to Pell's equation. The definition of Pell's equation is x squared minus dy squared equals 1, where x and y are positive integers, and d is a non-square positive integer. So you can see how this is a Diophantine equation, and the condition that d is non-square isn't obvious at the start, but we can have a look at why now. Because we know that d is, so if we say that d is a square number, we can say that d equals k squared, where k is a positive integer. And here we've just substituted k squared in for d at the top, and we can use difference of two squares to get that x plus ky times x minus ky is equal to 1. And because we know that x, k and y are all integers, and the only pairs of two integers that can multiply to get 1 are 1 times 1 and minus 1 times minus 1. But because x, k and y are all positive, this here will not work because x plus ky must be positive. And if they're both equal to 1, then x plus ky will be equal to x minus ky. But this, again, the x's here will cancel, and that means that 2ky is equal to 0, which is again not possible because k and y must be integers. So there are no solutions when d is a square, and that's why d must be non-square. We can use Pell's equation to approximate square roots as well, because we can rearrange that equation there to get that the square root of d is equal to the square root of x squared minus 1 over y squared. And as x and y become large, this is approximately equal to x squared, the square root of x squared over y squared, which is x over y. Because when x and y are large, the minus 1 on the numerator doesn't really make much difference. So there are many ways you can go about solving Pell's equation. And the first one is called the brute force method. And I think some of you might be able to guess what this means. Does anyone have any idea how, if we were given D, we could solve this? Yeah?
Just plug in numbers in like a sequence and see which ones work.
Perfect, yeah. So we can make this easier for ourselves by rearranging like this. And we can do an example where D equals 5. So, opening the board. Right. Okay. If we try, so our equation, if D equals 5, is x squared equals 5y squared plus 1. And we can start trying values of y and see if we get a square number on the other side. So first we can try y equals 1. That seems quite sensible because we know that y must be a positive integer. And if we plug y into 5y squared plus 1, we get 5 times 1 squared plus 1, which is equal to 6, and that's not a square, so that won't work. And then trying y equals 2, you get 5 times 2 squared plus 1, which is equal to 21, which is again not a square number. And I think, if I remember correctly, that y equals 4 will give us the right answer. Yeah, because 5 times 4 squared plus 1 is equal to 81, and that means that x will be 9. And that is our first pair of solutions that we can get using the brute force method. Okay. If we try using the same method when d equals 13, the smallest value of y that returns a perfect square for x squared is 180, and you can see how that might take a long time to find. And so it's not very efficient. So we can, the equation that the solution to the equation that we found when d equals 5, the first pair, which is x equals 9 and y equals 4, that is called our fundamental solution. So the first solution that we come across, or the pair of the minimum values of x and y. So that's the smallest value of y that will give an integer value of x there. And a method that we can use to find the fundamental solution without using trial and error involves continued fractions. So this is an example of a continued fraction here, and a little bit of notation. We can write this continued fraction using square brackets and with a semicolon, so that A0 represents the non-fractional part, the integer part of the continued fraction. And we can say that all irrational square roots have a continued fraction expansion. So for example, taking the square root of 6, we can write that as 2 plus the square root of 6 minus 2, because 2 is the integer part of root 6. So if you take the decimal expansion of root 6, I think it's 2 point something something something. And so we can take that integer part out, and we can then multiply root 6 minus 2 over 1. We can multiply both top and bottom by root 6 plus 2. Like that. And we get, after expanding brackets, 2 plus 2 over the square root of 6 plus 2. And we can write this fraction as 1 over the reciprocal of that fraction. You can just see by dividing by 2 on top and bottom. And we can repeat the same process with this bottom part here. we can say that this, the root 6 plus 2 over 2 is equal to the root of 6 minus 2 plus 4 over 2, and that is equal to root of 6 minus 2 over 2 plus 4 over 2, and that's where we get the plus 2 over here from. We can continue, and you can see how this will carry on forever, and that's where we get our continued fraction expansion from. So this can be repeated with any square root, and we can say that it will repeat after a certain number of partial denominators. The partial denominator is just these denominators here. And we can write the square root of 6 using the notation we saw before. Or we can use, as you might have seen with decimal expansions, you can use a repeat bar over the top of the partial denominators that repeat. And now, just a quick detour into why you can write every square root as a partial, square root expansion. So if we call the root of 6 x, we can see that this part here is also equal to x, because this part is going to still be 1 plus 2 over 1 plus 4 plus 1 plus 1 over 2 plus and so on. So we can replace this part here with x, and then we can solve this now to find what x is. So multiplying both sides by the denominator, we get 2x plus x over 4 plus x is equal to 1, and expanding and multiplying both sides by 4 plus x, you can see that this will result in a quadratic, and that's where we get the root, the irrational square roots from. Now there are some things we can say about continued fraction expansions of the form there. For some k, we can say that the integer parts of the continued fraction expansion will be the floor of the square root of d. This notation here means the integer, which is the largest integer that is smaller or equal to this number here. So the floor of 2.5 would be equal to 2, because 2 is the largest integer that is smaller or equal to 2.5. We can say that AK, so that last repeating partial denominator, is equal to twice the integer part of the continued fraction expansion, and that the repeating partial denominators up to AK minus 1 form a palindrome. So that is A1 is equal to AK minus 1, and A2 is equal to AK minus 2, and so on. Finding fundamental solutions, we can use this here to find our fundamental solution. So this looks quite complex initially, but we can simplify what this is saying. So we can have a look at an example. I think that will clarify. Find the fundamental solution to Pell's equation, where d equals 3, given that the square root of 3 has this continued fraction expansion. So our first step is, we know from these rules down here, this is A0, this is A1, and this is A2. And so AK is equal to 2. Sorry, K is equal to 2, I think. K is equal to 2. So that's A0, A1, A2, so k is equal to 2, because this is the last part of the denominator. And because k is equal to 2, we know that k is even, and so x over y will be equal to this continued function expansion here. So we can say that because k is even, x over y is equal to, so k minus 1 is just a1, so that would be this term here. So x over y is equal to a0, a1, which is 1, all the way up until a to the k minus 1, which is just a1. So that's it. And this is equal to 1 plus 1 over 1, using the notation that we saw before. And that is equal to 2 over 1, or just 2. And so we can see that our solution, our fundamental solution, is x is equal to 2 and y is equal to 1. And we should be able to check that in our equation. So x squared minus d3y squared is equal to 1. X is equal to 2, so 2 squared minus 3 times 1 squared is equal to 1, as we need. One more equation, one more example. Here, d equals 13, and the continued fraction expansion is here, and we can see that k is, so this is a0, a1, a1, a2, a3, a4, and a5. So here k is 5 and k is odd. So our continued fraction expansion for x over y will be a0, a1, a2, all the way up until a to the 2k minus 1, which in this case will be 2 times 5 minus 1, which is 9. So 3, 1, 1, 1, 1, that's up until a4, that's a5, and then repeats, a6, a7, a8, and a9. And that should give us our x over y, and that is equal to 649 over 180. And so x is 649 and 180 is y. And we'll always take x over y in its simplest form to get our fundamental solution. And we can manipulate Pell's equation and use our properties of surds to gain more solutions when we know our fundamental one. So we can, because we can split d into the square root of d squared, we can write this as a difference of 2 squares. So that would be x minus y root d times x plus y root d. That will be equal to 1. And we can raise both sides of this equation to the power, let's say, p. So if we do that, we'd get x minus y root d to the p times x plus y root d to the power p. And that will equal 1 to the p, which is just equal to 1 still. So we can see that this will give us another solution to Pell's equation, because if we expand out the brackets for something like 2 plus 3 root 2, if we say that's squared, when we expand out these brackets, we will get 4 plus 6 root 2 plus 6 root 2 again, and then plus 9 root 2 squared. And this here is also an integer because root 2 squared is just 2. So that'll be 4 plus 9 times 2, which is 4 plus 18, so that's 22, plus 12 root 2. And you can see that if we raise any sort of surd like x minus y root d or x plus y root d to any power, we'll always get another surd of that same form. So if, say, 2, 3 was a fundamental solution to a Pell's equation, then 22, 12 will also be another fundamental, or not the fundamental, another solution to Pell's equation. This should be written up neatly on the next slide. There you go. So this is our fundamental. This x0 and y0, that is our fundamental solution. And raising that to the power p, we can gain another solution to Pell's equation, which we will call xp, yp, for different powers of p. So we can see that there are actually an infinite number of solutions to Pell's equation. And we can rearrange the equations we saw before. So we can add equations 1 and 2 together, and that will cancel out these yp square root d terms, and we'll get 2xp is equal to x0 plus y0 root d to the p plus x0 minus y0 root d to the p. And so we can divide by 2 to see what our xp is in terms of our fundamental solution and the p that we've raised our surd to. And we could do the same for equation 1 minus equation 2. So we can cancel out the xp terms, and we can gain an equation with yp as its subject. And these formula make finding additional solutions to the equation very easy once you know what your fundamental solutions are. And we can also consider another equation, similar to Pell's equation. So that's x squared minus dy squared is equal to minus 1 instead of 1. And solutions only exist when k, which we saw before, this is the period of the continued fraction expansion. And that only exists when k is odd. And we can get similar results as before for x over y. So one last example with d equals 13, the negative Pell's equation. So this here, a0, and we go up here 1, 2, 3, 4, a5. So our k is equal to 5, which is odd, so that fits our criteria. And a to the k minus 1, that is a4. So x over y is equal to a0, a1, a2, a3, a4. And that is equal to 18 over 5. And checking that in our negative Pell's equation will give minus 1. So 18 squared minus 13 times 5 squared will be equal to minus 1. And finally, our generalized Pell's equation is an equation of that form on the board there. So x squared minus dy squared equals some integer n. And this equation can be solved by considering a Pell's resolvent equation. So for an equation x squared minus dy squared equals n, we can define a Pell's resolvent equation to be u squared minus dv squared is equal to 1. So this would be more like our previous Pell's equation, but with the same x and y, u and v, but it's equal to 1 instead of n. This will be, so we're solving, I'll give you an example. If we're trying to solve x squared minus 5 squared is equal to n, then we could consider the Pell's resolvent equation, u squared minus 5v squared is equal to 1, and solve this equation like we would the previous Pell's equation. And we can use this Pell's resolvent equation, once we have fundamental solutions to that, to this one. So all we have to do is find one fundamental solution to that Pell's equation up there, and we can use all of the solutions to the Pell's resolvent equation to form more solutions. So this here is how we generate more solutions for the generalized Pell's equation. So here we can see this is the solutions to our Pell's resolvent equation, and we can use our fundamental solution for the generalized Pell's equation with the solutions to the resolvent one to gain more solutions to the generalized one. And I'll show you why this works on the next slide. So here we can say that we can expand this right hand side here. So we would get x0 un plus x0 bn root d plus y0 root d un plus y0 root d times vn root d. And we can simplify that to get x0 un plus y0 vn d plus x0 vn plus y0 un, and that's square root d. And so sorry for my messy handwriting. We will be able to further simplify this. I might move over to the whiteboard. Do you know if there's a whiteboard rubber? Can you? Oh, yes, please, that'd be great, thank you. Just start in the corner. So we've got x0 un plus y0 vn d plus x0 vn plus y0 un root d. Okay, so that's what we've got on the board there. We can then plug this in, because you know this is equal to xp plus yp root d. So we can compare coefficients and say that this part here is equal to xp and this part here is equal to yp. And we can then plug these expressions for xp and yp back into here. Thank you. Doing that, you should get some cancellations. Right. So now we can plug that into our original Pell's equation, Pell's generalized equation, equal to n. So we can plug this xp and this yp into here. So we would get x0 un plus y0 vnd, that's our xp squared, minus d yp, yp is this x0 vn plus y0 un squared, and that should be equal to n. We can then expand out these brackets, which I won't do here because it's very messy. But once we've done that, we can collect terms to get x0 squared, un squared minus dv n squared, and that is minus dy 0 squared, un squared minus dv n squared, and that is equal to because we can see. Does anyone notice anything about these brackets here? Un squared minus dvn squared. Yep.
The same.
Do you know? Do you remember this equation that we had before, the Pell's resolvent? U squared minus dv squared equal to 1.
Yeah.
Do you remember? Did you see how this links to here? So you can see, because un and vn are solutions to this equation, we know that un squared minus dvn squared will be equal to 1. So we can see that this is equal to x0 squared, because this is 1, this doesn't matter, minus dy0 squared. And this, because we know that x0 and y0 are fundamental solutions to our equation x squared minus dy squared equals n. Because x0 is x0y0 is a solution to this equation here, we can see that this will also be equal to n because of how we defined our fundamental solution. So we can see how using this, we can gain another solution to the generalized equation using the Pell's resolvent and the fundamental solution to that first equation. Thank you for listening.